Travis. Hi, Wayne. This is John Whitaker for the Probability Graduate Level class, and this is our 28th video lecture. And today, during this lecture, what I want to do is give some examples of where we use that corollary to the compound random variable identity, as well as using that fact that we had about Poisson random variables. So if n was Poisson, then n minus 1 would be Poisson, where m satisfied that particular characteristic that was needed for that corollary. Let's start off with an example. We're going to do a similar type of fact that we did for Poisson random variables with binomial, and then do an example of that. So today is going to consist of 2 examples and 1 fact. That's it. And of course, everything's based on that corollary for the compound random variable identity. So here's the example I want to look at. It says, let S of n be a compound random variable with n being Poisson with mean lambda equal to 4. Let the probability that x of I equals to 1/4 for I equaling 1, 2, 3, and 4. Okay. Find the probability that S of n is equal to 5. Okay. In this problem, we're going to use, as I said before, that corollary to the compound random variable identity, and also the fact having to do with n being Poisson. Okay, so here's what we notice. Since S of n is a compound random variable, then we have a sequence. X of 1, X of 2, forever, of independent and they're going to be identically distributed random variables. Okay, that's what we're looking at with those, with that sequence, x of 1, x of 2, of random variables, so on. And so, since we're having in our problem that the probability of x of I equaling to I is equal to 1/4, and that's true for I equaling 1, 2, 3, and 4. Okay, then we have the probability that x of 1 equals to 1 equals to 1/4. That's what this means. The probability that x of 2 equals to 2 equals to 1/4. The probability that x of 3 equals to 3 equals to 1/4. And finally, the probability that x of 4 equals to 4 equals to 1/4. Now, let's don't forget these sequence of random variables are identically distributed. And so, let me write that down. We can describe the PMF for each one of these random variables. So since x of 1, x of 2, and so forth are identically distributed, then for any q of the natural numbers, I'll say, script n, we have a probability that x of q equals to 1 equals to 1/4. The probability that x of q equals to 2 equals to 1/4. The probability that x of q equals to 3, that's equal to 1/4. And we have the probability that x of q equals to 4, that's equal to 1/4. And the probability that x of q equals to some number bigger than that, let's say z, is equal to 0 for z, yes, for all z element natural numbers with z being greater than or equal to 5. Okay. Now, we'll note that x of q, that's always greater than 0, so they're always positive. So applying the previous corollary, okay, here's what we have. The probability, this is our problem, S of n is equal to 5. Okay, that's our problem. Well, let me write down the corollary. S of n is equal to k. Remember what that was. It's 1 over k, the expected value of n, times the sum, we're going to use this a lot, and j runs from 1 to k. Here it was j, and then it was the probability that x of 1 equals to j, okay, times the probability that s of m sub 1 equals to k minus j, and remember that m sub 1 had that, m had that, was a random variable, had that special quality, okay? Special relationship in terms of its probability that m is equal to a little number n, related to big N. Okay? So, the probability that S of n equals to 5, that's going to be equal to 1 over 5 times the expected value of n times the sum as j runs from 1 to 5 of the probability that x of 1 equals to j times the probability that s of m minus 1 is equal to 5 minus j. Okay, in our problem, the expected value of n, remember it was Poisson with lambda equal to 4, so this is equal to 4/5, if you will, because the expected value of n is 4. And then here, this will be the sum, and I'll just write this down. As j runs from 1 to 5, probability of x of 1 equal to j times the probability of s of m minus 1 equal to 5 minus j. What we're going to get in this example is the iterative effect of our corollaries formula, okay? Along with that fact that we had involving Poisson random variables. Okay, what I mean is the following. So that's equal to, what we're working on is equal to 4/5 times, okay, you know, in my work here, I made a mistake. Let me make a correction. Let's go back here. I made a mistake here. Here's the J, and I forgot it here. So here's a J, here's a J. Okay? Made a mistake. Make that correction. So here, as we use that formula, this will be 4/5 times 1 times the probability that x of 1 is equal to 1. Well, that's 1/4. Times the probability that s of m minus 1 is equal to 4. And then plus, it'd be 2 times the probability that x of 1 is equal to 2. Well, that was 1/4. Times the probability that s of m sub 1, m minus 1, is equal to 3. Plus, okay, the probability, so this will be, again, we have 3 times 1/4 times the probability that s of m minus 1 is equal to 2. Plus 4 times 1/4 times the probability that s of m minus 1 is equal to 1. Okay. And then plus, here it would be 5 times 0 times the probability that s sub m minus 1 is equal to 0. And that's what it is. And I get 0 here because the probability that x sub 1 is equal to 5 is 0. Well, we're going to calculate this anyway. So the probability, because we're going to need it, that s of m minus 1 is equal to 0. Okay. Well, that was equal to the probability that n was equal to 0. And the probability that n is equal to 0. Remember, m was Poisson distributed, so this was part of a corollary. It's Poisson distributed with parameter lambda equal to 4. So this is e to the minus 4, lambda, that's 4, raised to the x, that's 0, over 0 factorial. And so we just get e to the minus 4. Okay? So this part was part of the corollary. All right? Now, the probability that s of m minus 1 equals to 1, well, this right here is a Poisson random variable with parameter lambda, so 4. So here's what I get. I use my corollary again. The answer to this, okay, so this is an index, and what I would have is 1 over k, so that's 1, the expected value of m minus 1, times the sum as j runs from 1 to 1 of j times the probability x of 1 equals to j times the probability of s of m sub 1 minus 1 is equal to k, which in this case is 1, minus j. Okay, so that's what I have. Okay, now, this is 1 over 1. Here, this number right here is 4. Okay, by the fact that we had earlier last time. And then here, this is just going to be 1. There's only one term here. This is 1/4. The probability that x of 1 is equal to 1. And then the probability that S of M sub 1 minus 1 is equal to 0, well, M sub 1 minus 1 is still going to be a Poisson random variable. Okay? It's still going to be a Poisson random variable with parameter lambda. And it ends up being the same thing as we have here. So I just get 4. So its parameter is 4. So I get the answer that I have here, e to the minus 4. Okay? So here's the formula. I know what to stick in here, even though I'm going to get 0. But now I know what to stick in here. It's this number. So that's just equal to e to the minus 4. Okay? Now, question is what do we have for the probability S of n minus 1 is equal to 2? So that's what I'm going to work on. And I kind of iteratively work my way towards each one of these probabilities to fill into the formula that we have in this line. Okay, so note the probability S of M minus 1 equals to 2, again, by our corollary. This is equal to 1 over the 2, the expected value of M minus 1 times the sum as j runs from 1 to 2 of j and the probability that x of 1 equals to j times the probability that some other random variable, m sub 1, minus 1, okay, is equal to k minus j, so that's 2 minus j. And that's what I have. This is going to be equal to 1/2, again, the m minus 1, because of the n being Poisson. We've got this m minus 1 is going to be Poisson parameter, the same thing as n, which was 4. So this expected value of that is 4. And then times this sum. So it's 1 times 1/4, because that's the probability that x of 1 is equal to 1. And then times the probability that S of m sub 1 minus 1 is equal to, well, when j is equal to 1, would be 1, plus, this would be, here I would have 2 times the probability x of 1 is equal to, which is 1/4, and now the probability that S of m sub 1 minus 1 is equal to, so this would be 0. Aha! I calculated that part earlier. Matter of fact, both of these happen to be the same. So this ends up being 2 times 1/4. Here this was e to the minus 4. We calculated that previously, where we just had m minus 1 instead of m sub 1 minus 1. But it turns out this is going to be Poisson with parameter 4. And same thing with this one. And so here we have 2/4 e to the minus 4, just as we calculated this before, but we had a probability of S sub m minus 1. But it's going to work the same with S of m sub 1 minus 1 because of the fact that we had involving Poisson random variables from our previous lecture. And so this ends up being 3/2 e to the minus 4. So that's what I know to stick in for part of where we were in calculating the probability that S of n was equal to 5. Okay? All right, now what we need to know is what's the probability that S of m minus 1 is equal to 3. That was part of that computation. And so here's what I want to say about that.
this is equal to, using our formula, 1/3 times the expected value of m minus 1 times the sum as j runs from 1 to 3 of j times the probability x sub 1 equals to j times the probability that s of m sub 1, m sub 1 minus 1 equals to 3 minus j. This will be 3 minus j. So here again, this is 4, so it's 4/3. And then I'm going to multiply this by 3 times 1/4. It's 3. 1 times 1/4 times the probability that s sub m sub 1 minus 1 equals to, so here it's 2 plus, it would be 2 times 1/4 times the probability that s of m sub 1 minus 1 is equal to, here I'd have 1 plus, it would be 3 times 1/4 times the probability that s of m sub 1 minus 1 equals to 0. We've already computed this part. Here's what I want to tell you, just in a different setting. It's 4/3. Now, this part, m sub 1 minus 1, is identical to this one, because the m sub 1 minus 1 will be Poisson parameter 4. So it's exactly the same thing as what we had here, which we found to be 3/2 e to the minus 4. Here, this is plus 1/2, I'll make it 2/4. And again, s of n sub 1 minus 1, we calculate s, the probability that s of m minus 1 is equal to 1, it's going to be identical here, and that was e to the minus 4, and this guy is plus 3/4, and the probability that s of m sub 1 minus 1 equals 0 is the same thing as probability of s of m minus, s sub m minus 1 equal to 0, which we found to be e to the minus 4. And so when we compute this, let's see, it's 3, 6, 8/4, so it's 4/3 times 8/4 times e to the minus 4, so what I end up getting here is 8/3, I think. Yeah, something's wrong here. Oh, what's wrong? Here, there's a mistake. So it's 1/4 times this. So this is 1/4 times this, okay. And here this is 2/4 times this part. So, yeah, I got this. Times s of m minus 1, which we just got to be e to the minus 4. I think that's right. So let me check my work here. Yes, it is. That's right. 3/4. That's right. So here, this is 4/3. Here, this happens to be 3/8. Yeah, this number's not right. Let me make the correction. So this is 3/8 plus, what number is this? This is going to be out of 8. It's going to be 4/8 plus, what number is this going to be? It's going to be 6/8. All that times e to the minus 4. And so that's equal to, let's see, this is going to be 3, 7, 13. 8 times 4/3 times e to the minus 4. And so what I end up getting here, this cancels out to 13/6 e to the minus 4. That's what I get for the probability that s of m minus 1 is equal to 3, which was part of our formula in calculating the probability that s of n was equal to 5. Okay. And so The last thing in our calculation, I believe, was the probability that S of m minus 1 is equal to 4. And using the corollary again, this is 1 over k, so it's 1 over 4, the expected value of m minus 1, excuse me, times the sum as j runs from 1, and here it would be to k, which is 4, of j times the probability that x of 1 equals to j, and that's going to be 4 over time, or 1/4 over time, times the probability that s of m sub 1 minus 1 is equal to k, which is 4 minus j. So this is equal to 1/4 times 4 times this sum. So this is 1 times 1/4 times the probability that s of m sub 1 minus 1 is equal to 3 plus 2 times 1/4 times the probability that s of m sub 1 minus 1 is equal to 2 plus 3 times 1/4 times the probability that s of m sub 1 minus 1 is equal to 1 plus, here this will be 4 times 1/4 times the probability that s of m sub 1 minus 1 is equal to 0. Okay. So this is 1. So we're just ending up with this sum. So it's 1/4, and the probability that s of m sub 1 minus 1 is equal to 3. We had m sub 1 minus 1. We computed for s of m minus 1, but it works the same for s of m sub 1 minus 1 because this is going to be a Poisson random variable m sub 1 minus 1 with parameter lambda. And so what we end up getting here was this 1/4 times 13 over 6 e to the minus 4 plus, this is going to be 1/2. Here we had computed this, and I think it was 3/2 times e to the minus 4 plus, this is 3/4. Let's make this 2/4. And then 3/4, and then this was e to the minus 4, and then finally plus e to the minus 4. Okay, I think that's what's involved. Okay, so when you do this work, let me check and make sure I didn't make a mistake. Okay, what this ends up being, so you can check this, this ends up being 73 over 24 e to the minus 4. So now we're ready to answer the question. Okay. So, the probability that S of n equals 5. Okay. Plug these into our formulas. 4/5. So what formula am I talking about? I am talking about this one. Okay, I'm not going to write it down again. It was 4/5 times a bunch of numbers, each one of them multiplied by the probability that S of m minus 1 is equal to 4, equal to 3, equal to 2, equal to 1, so forth. Okay? Okay, so here's what we get when we plug these in. It's 4/5 times 1/4, 73 over 24 e to the minus 4 plus 1/2 times 13 over 6 e to the minus 4 plus 3/4 times 3/2 times e to the minus 4 plus e to the minus 4 plus 0 And when you add all those up, what you end up getting is 381 over 120 e to the minus 4. Okay. Well, in that example we just had, we had that n was Poisson, and we had a particular parameter, lambda 4. Well, we used the fact for Poisson random variables, and we're now going to write down a similar fact and prove it for binomials. So here's what it says. It says let n be a binomial random variable with parameters R and P. Let M be a random variable such that the probability that M is equal to N is equal to N times the probability that N is equal to N all over the expected value of N, with N running from 1, 2, 3, so forth. Then we're going to talk about M minus 1. M minus 1 is a binomial with parameters R minus 1 and P. So R minus 1 is how many times we're doing this. So let's do the proof. Let's let N be a binomial random variable with parameters R and P. So P is the chance of success. R is the number of times we'll do the trial. Or let M be a random variable with the probability that M is equal to N equals to N times the probability that N is equal to N over the expected value of N. For this is N running from 1, 2, 3. Now, so for N equaling 0, 1, 2, and so forth, the probability that M minus 1 is equal to N, so we want to show that this is binomial. Well, that's equal to the probability that M is equal to N plus 1. And so we have that formula relating it to N, and so we use that in from our hypothesis. Okay. So that's equal to N plus 1 times the probability that N is equal to N plus 1 over the expected value of N, and that's equal to N plus 1. Now, N was binomial, and so with parameters R and P. So what we get here is that R choose N plus 1, P to the n plus 1, 1 minus P to the, it would be R minus n minus 1, all over, the expected value of n is R times P, because it's binomial, the parameters are P. This is equal to n plus 1 times R factorial over n, or R minus n minus 1 factorial, all over n plus 1 factorial. Here it's P to the n plus 1. Well, that's one of the P's in the top cancels with the P in the bottom. So we're just left with, in the top, P to the n. We have an R sitting here, and then we have 1 minus P raised to the R minus 1 minus n. That's what I write. The n plus 1 here and the n plus 1 there will cancel. There's an R here and an R there that will cancel. So if you will, I'll write down R minus 1 factorial over, this is R minus 1 minus n, is the way of writing it, factorial. Here we'll just have n factorial. That R canceled with one of these R's to make R minus 1. This is P to the n. One minus P to the R minus 1 minus n. Now, that's equal to, so one more, so what we have is the probability that m minus 1 equals to n. Okay? That's equal to, this is R minus 1, choose n. That's what that is. P to the n, 1 minus P to the R minus 1 minus n. So, m minus 1 is binomial because it's PMF has the right form with parameters so it's R minus 1 and P have the right form. And that's what we were setting up to prove. Now I want to use our corollary along with this fact, as opposed to the fact that we have about Poisson, to do an example. And the example we're about to do is much more complicated than the previous example in that the iterative effect involves more calculations. So the iterative effect of that corollary, because of using maybe a binomial random variable, is going to cause more computation to be done. So let n be a binomial random variable with parameters R and P. Let S of n be a compound random variable where S of n is, of course, defined as I runs from 1 to big N of x of I, okay, with x of i's, or x of 1, x of 2, and so forth, being a sequence of independent and identically distributed random variables. and being independent of the sequence of x of 1, x of 2, and so forth. A little bit more notation. Oops, sorry. We're going to let p sub x sub 1 equal to j equal to alpha sub j in this problem. And so find the probability that s of n is equal to 3 in terms of alpha sub j, r, and p. Okay, much harder problem than the previous problem we had. All right, so here's what it says. Well, note by our corollary. We will be using this corollary again several times. The probability that s of n equals to 3 is equal to 1 over 3, the expected value of n, times the sum as j runs from 1 to 3 of j times the probability that x of 1 equals to j times the probability that s sub m, that's what I write, minus 1, is equal to k, which is 3 minus j. That's what we have to do. So this is equal to, okay, this is 1/3. Now here, the expected value, and we knew n was binomial with parameters r and p, so this is r times p. This sum would be 1 times the probability x of 1 is equal to j, which is equal to alpha sub 1, times the probability that s of m minus 1 is equal to 2, plus 2 times alpha sub 2 times the probability that s of m minus 1 is equal to 1, plus 3 times alpha sub 3 times the probability that s of m minus 1 is equal to 0. Okay, this first guy is easy to compute. Note, so this is the formula we'll come back to, okay? Let me make sure I didn't make a mistake. No, I didn't make a mistake. Now, the probability that s of m minus 1 equals to 0 is the same thing as the probability that n equals to 0. So that's 1 minus p. So what would this be? R choose 0. Okay, that's just 1. Then it'd be p to the 0. That's just 1. Then it'd be 1 minus p to the n minus 0. I'm sorry, not n, but r minus 0. So I just get r. Except it's... Wait a second. Wait a second. This is going to be, I should write this down. This is equal to the probability that m minus 1, that's what this is. I made a mistake. This is the probability equal to 0 of this index random variable equaling to 0. Okay? Okay, now, I made a mistake. So here, this is again binomial with parameters r minus 1 and p. And so what I end up getting is r minus 1 choose 0, that's just 1. A p to the 0, that's just 1. And here's 1 minus p to the r minus 1. So here, remember, the fact was the probability of S of n equal to 0 is the probability of n. I made a mistake here. We're not dealing with n, we're just dealing with n minus 1. That's from the corollary. Okay, so we have this guy right here to stick in. We need this and this. Computation still to be made. When we were working with, don't forget this, when we were working with Poisson random variable, when you still had that m involved, or that other function that had the relationship between the probability of that random variable is equal to n, with the involving probability, the big N is equal to that little n. Remember, with Poisson, we still had the same parameters. Here, we're still getting binomial, but they don't have the same parameters. So it's going to cause us to do some computations. So let's note the probability that S of m minus 1 is equal to 1. Now, by our corollary, that's 1 over 1 times the expected value of m minus 1. Right, times the sum, as j runs from 1 to 1 in this case, of j probability that x of 1 equals to j, and then times the probability that something else, s of m sub 1 minus 1, is equal to k, so that's 1 minus 1 minus j. And this guy right here, so this is equal to, if you will, 1, what's the expected value of n sub 1? Well, m sub 1 is going to be binomial with parameters r minus 1 and p. So here, this is going to be 1 times r minus 1 times p. Here, we're only going to have one thing, one term. So there's 1. This is alpha sub 1. And now the probability that s of m sub 1 minus 1 is equal to, here, 0. Okay. Now, we had m minus 1 was binomial with parameters r minus 1 and p. M sub 1 minus 1 is now going to be a binomial with parameters r minus 2 and p. And so here, this is equal to r minus 1 times p times alpha sub 1. Here, this is going to be times 1 minus p to the r minus 2. That's what we should get. Okay, let me check. Make sure I haven't made a mistake. Yes, that's right. All right. Okay. Now, note, the next thing we need is the probability that s of m minus 1 is equal to 2. Well, that's going to be equal to, by our corollary, 1 over 2, expected value of m minus 1, times the sum, as j runs from 1 to 2, of, here's j, alpha sub j, if you'll allow me to write that, and then the probability that s of m, I'll say sub 1 minus 1 is equal to 2 minus 1. Okay. This is equal to 1/2 times, here's r minus 1 times p, times, here's alpha sub 1, probability that s of m sub 1 minus 1 equals to 1 plus, here it's going to be 2, alpha sub 2, times the probability that s sub m minus 1 is equal to 0. Okay. All right, now this is something maybe not so hard to calculate. That's okay. So here, this is equal to 1/2 r minus 1 times p times alpha sub 1. Now, what's this probability? Well, we use the corollary again. This is my k. So it's going to be equal to 1 over 1 times the expected value of m sub 1 minus 1 times the sum as j runs from 1 to here k is 1. So I only got one thing. Here I'm going to have j, alpha sub j, and one thing. And then this will be the probability that s sub m sub 2 minus 1 is equal to 1 minus j plus, this is 2 times alpha sub 2. Now this guy is, okay, so let's see. N has parameters r and p. M has parameters, or M has parameters R, or M minus 1 has parameters R minus 1 and P. M sub 1 minus 1 has parameters R minus 2 and P. So the chance that this is equal to 0, again, is 1 minus P to the R minus, I think, 3. Let me check. No, it's R minus 2. Yes, R minus 2. That's right, that's right. Okay, so let's keep working. Almost done. R minus 2. That's right. Okay. That's good. And so now what we need, we get this is equal to 1/2 R minus 1 times P times, this is alpha sub 1. Here, the expected value of M sub 1 minus 1. So it's R minus 2, I think, times P. Let me check. Yep, that's right. And then there's one more term in this sum here. And so it's the probability, I'm going to write this down, that S of M sub 2 minus 1 is equal to 0. That's what this would be. Plus 2 times alpha sub 2, and here this is 1 minus P raised to R minus 2. Okay, this is going to be binomial, the M sub 2 minus 1 is going to be binomial with parameters R minus 3 and P. So this ends up being 1/2 R minus 1 times P times alpha sub 1 times R minus 2 times P. This ends up being 1 minus P to the R minus 3 plus 2 times alpha sub 2 times 1 minus P to the R minus 2. Okay. So, the probability that S of n is equal to 3 is equal to, well, it's a mess, but it's 1/3 RP times alpha sub 1 times this one, 1/2 times R minus 1 times P times, it will be alpha sub 1 squared times R minus 2 times P to the 1 minus P to the R minus 3. Yeah, I have more. Plus, still involved in that parentheses, okay? Plus 2 times alpha sub 2 times 1 minus P raised to R minus 2 in that parentheses. That's that part. Okay? That's what we just had here. I've got more. All right, plus, so inside still this bracket, 2 times alpha sub 2 times alpha sub 1 times r minus 1.
You know what, let me write it down here.
Plus 2 times alpha sub 2 times alpha sub 1 times r minus 1 with p times p times 1 minus p raised to the r minus 2. That ends that parenthesis, that quantity. And then plus 3 alpha sub 3 times 1 minus p to the r minus 1. And when you keep working with that, here's your final answer. Okay, it's a mess, but this is what it looks like. It's equal to 1/3, so algebraically, RP times alpha sub 1 over 2 times R minus 1 times P times this quantity, alpha sub 1 squared P times R minus 2 times 1 minus P to the R minus 3 plus 2 alpha sub 2 times 1 minus P to the R minus 2 plus RP times 2 alpha sub 2 over 3 times R minus 1 times P times, I think it's alpha, I think it's sub 1. No, it's not alpha sub 1. Must be alpha sub, I don't know what it is. I made a mistake in my notes here. We'll leave it blank. 1 minus P to the R minus 2, alpha sub 3, R times P times 1 minus P to the R minus 1. Okay? So I just simplified it, but I've forgotten what this alpha sub is. Let's see if I can do it. Alpha sub 2. I think this is alpha sub 2. Yeah. I'm looking at it. It's alpha sub 2. I got it. That's what it is. Thank you very much. That concludes the solution to this problem and our solution and this video.